A particle of light is traveling toward you from a place you cannot see. This is the story of a photon's incredible journey, a voyage from the core of a star to the back of your eye. By the end, you will understand your own vision as a cosmic meeting point with deep time. What ancient transformations must that light undergo before it becomes a thought? And why does its path connect you directly to the heart of a distant sun? How does it feel to know you are the destination for a traveler that began its life before human history? This journey begins in a cauldron of unimaginable power. Picture the very center of a star like our own sun, a place where the weight of the entire star presses inward with relentless force. This is not empty space. It is a realm of such intense pressure and heat that the very rules of matter as we know them are rewritten. Here, hydrogen atoms, the simplest and most abundant building blocks in the universe, are stripped of their electrons and squeezed together by gravity's immense hand. They are forced so close that their nuclei, which normally repel each other with fierce electrical force, are slammed into union. This is the stellar forge, the engine of every star, where nuclear fusion unfolds. In a process that repeats countless times every second, 4 hydrogen nuclei are fused together to create one nucleus of helium. But here is the crucial mystery, the entire reason our story exists. When that new helium nucleus forms, it actually weighs slightly less than the 4 hydrogens that made it. A tiny fraction of mass simply vanishes, but according to the laws of physics, nothing is ever truly lost, it is only transformed. That missing mass becomes pure energy, a release of power described perfectly by Einstein's famous insight, that energy equals mass times the speed of light squared. Because the speed of light is such an astronomically huge number, even a minuscule amount of mass converts into a staggering burst of energy. This energy first appears as a furious flash of gamma radiation, the most energetic form of light in the cosmos. In that instant, our photon is born. It is not yet the gentle sunlight that warms your skin. It is a raw, primal scream of energy unleashed from the heart of matter itself. And from the moment of its creation, it is trapped. It now faces its first and perhaps greatest trial, a desperate struggle to escape the very star that gave it life. Trapped within a sun, the newborn photon begins an odyssey of pure chaos. This is not a straight line toward freedom, but a staggering, drunken stumble through an unimaginably crowded prison. Picture the very center of the star not as empty space, but as a substance more dense than lead, a seething plasma of atomic particles packed so tightly they are practically touching. Our gamma ray, the most potent form of light, cannot simply race outward. It zips forward for a fraction of a centimeter, less than the width of a pencil lead, before it smashes directly into a proton or a free electron. In that instant, the photon is not reflected, it is consumed. The particle that absorbed it becomes excited, jittery with the new energy, and almost immediately spits out a new photon to regain its balance. But this new photon is often slightly less energetic, and it flies off in a completely random new direction. Physicists call this process a random walk, and it is the defining struggle of light's youth. Each absorption and re-emission is a tiny step in a journey with no map, a cosmic game of pinball where the bumpers are atomic nuclei, and the only rule is chance. Over and over, trillions upon trillions of times, this cycle repeats. The photon is passed from particle to particle, losing a whisper of its ferocious energy with each handoff. That raw, primal gamma ray is gradually tamed, stepped down first to a still powerful X-ray, then to an ultraviolet photon, and finally, after an almost incomprehensible span of time, into a particle of visible light. This diffusion process is so slow that the trip from the stellar core to the surface can take tens of thousands of years, sometimes even millions. All the while, the photon's path is randomized beyond any trace of its origin. The sunlight that finally reaches the surface carries no direct memory of the specific fusion event that created it, no story of that one violent birth. Instead, it carries a collective signature, a statistical average of the core's immense heat and pressure, smoothed out by an eternity of collisions. Having spent millennia in a desperate, zigzagging crawl, our photon, now a humble particle of visible light, finally reaches the star's outer layer, a region called the photosphere. Here, the density of matter finally thins out enough for a miracle to happen. The photon travels a full kilometer, then 10, then 100 without a single collision. For the first time in its existence, it is flying through what is essentially empty space. It has broken free from the pinball machine and is now streaking unimpeded into the void. But this newfound freedom is just the beginning of the next, even more perilous leg of its journey across the interstellar sea. Freedom is a sudden and silent shock. After tens of thousands of years of constant, violent collision, the photon now encounters nothing. It has reached the star's photosphere, the final thin skin that marks the boundary between the furnace within and the endless cold without. Here, the density of matter drops away so dramatically that the photon can travel for hundreds of kilometers without hitting a single atom. The random walk, that cosmic game of pinball, is over in an instant. The last interaction with its parent star is a gentle farewell, a final scattering that sets its course irrevocably outward. This final brush with the photosphere's atoms does one more crucial thing. It stamps the photon with its ultimate identity. The temperature of this glowing surface, around 5,500 degrees Celsius for our Sun, determines the precise wavelength, the exact color, of the escaping light. Every photon that slips free carries this thermal signature, a collective memory of the star's surface heat. This is why our Sun glows with that specific yellowish-white hue. It is the color of a 5,500-degree object. And in that glow is a hidden marvel of deep time. The sunlight striking your skin at this very moment is not a uniform wave from a single instant. It is a chaotic choir of individual travelers. Each photon, now racing alongside the others, began its random walk at a different moment in the star's history. Some may have started their journey when early humans first mastered fire, others when the pyramids were being built. They have all been queuing up in that dense interior, completing their staggering zigzag paths at different rates, only to burst free together into the same present moment. Their simultaneous escape creates the steady, constant stream we perceive as sunlight. With its prison break complete, the photon is now truly on its own. It crosses the photosphere's threshold not with a sound but with a burst of pure motion. Instantly, it accelerates to the universe's ultimate speed limit, 299,792,458 meters per second. It is now a citizen of the interstellar void, a speck of ordered energy racing in a perfect, unwavering line through the profound emptiness between stars. But this straight line is not a safe passage, it is a gauntlet. Ahead lies an 8-minute voyage across 150 million kilometers of space, a journey that will test the photon's integrity against the very fabric of the solar system itself. 299,792,458 meters per second is not just a speed, it is a law of the cosmos. Our photon, now a citizen of the void, obeys this law perfectly. For the first time since its violent birth, its path is not a zigzag but a ruler straight line through absolute emptiness. This is the cosmic marathon, a sprint across distances so vast they defy human intuition. From our Sun, this sprint lasts for 8 minutes and 20 seconds. Think of that, the light warming your face left its star a little over 8 minutes ago. You are seeing the sun not as it is now, but as it was during the last few minutes of your morning. Yet this is just a local commute. For a photon bursting free from the red supergiant Betelgeuse in the constellation Orion, the journey to Earth takes not minutes but centuries. The light from that star that you see on a clear winter night began its lonely voyage when telescopes were first being pointed at the heavens, when the scientific revolution was just a whisper. It has been traveling untouched and unchanged through the silent dark ever since. During this unimaginable voyage, the photon is far more than just a point of light. It is a meticulously encoded messenger. Locked within its specific wavelength is a story. That story contains the exact chemical signature of the star's outer layers, a readout of its surface temperature, even clues to its age and whether it is moving toward us or away. The photon carries this data with perfect fidelity, a natural hard drive of stellar information. And here is one of the most profound truths of its journey. For the photon itself, time does not exist. According to Einstein's theory of relativity, as an object approaches the speed of light, time for that object slows to a stop. From the photon's own perspective, if it could have one, its departure from the star's surface and its arrival at your eye are not two separate events centuries apart. They are the same instant. The entire marathon across the light years is compressed into a single, timeless moment. For us, the observers, the journey is measured in years. For the traveler, the journey is measured in exactly nothing. This period of pristine, unimpeded flight seems like a guarantee of a pure message, but the void between the stars is not truly empty, and it is far from passive. This straight line is a highway where cosmic forces lie in wait, forces that can intercept our silent messenger and subtly rewrite the story it carries before it ever reaches its final destination. That pristine straight line is an illusion of the void. The space between stars is not a perfect vacuum. It is a diffuse ocean of matter and force. Our photon, now a seasoned traveler, must navigate this subtle but treacherous medium. Its first common obstacle is something both beautiful and obstructive: interstellar dust. Picture not coarse sand, but particles finer than smoke, a haze of carbon and silicate minerals forged in the fiery depths of ancient stars. These dust grains drift in vast, cold clouds that can stretch for light years. When our speeding photon slams into one of these microscopic obstacles, it does not simply stop, it is redirected. This is called scattering, and it has a profound color-coded effect. Shorter wavelengths of light, which we perceive as blue, are much more easily knocked off course by these tiny grains than longer, redder wavelengths. It is similar to why our sky is blue. Sunlight scatters off molecules in our air, bathing the heavens in that familiar hue. On a cosmic scale, this means that as starlight passes through great dust clouds, the blue light is preferentially scattered away, leaving the surviving beam noticeably reddened. Astronomers call this interstellar reddening, and it is why many distant stars appear as faint crimson embers in our telescopes. But these clouds are not just filters, they can also become canvases of light. If the dust cloud is near a bright, hot star, the scattered blue light can make the entire nebula glow with an ethereal azure radiance. Other nebulae, rich in specific gases like hydrogen, might glow a deep red when energized by starlight. Every interaction, every scattering event subtly alters the photon's message. It arrives not as a pure signal from its star, but as a modified one, bearing the fingerprints of every cloud it has passed through. Yet an even more dramatic force can alter its path, one that bends not just light, but the very stage upon which it travels. According to Einstein's theory of general relativity, massive objects do not just pull on things with gravity, they warp the fabric of spacetime itself. Think of spacetime as a taut, flexible sheet. Placing a heavy weight like a galaxy or a black hole on that sheet creates a deep dimple. When our photon travels near such an object, it follows the curvature of this dimple. From our perspective, the light's path appears to bend, as if passing through a lens. This is gravitational lensing, a cosmic mirage of incredible power. A massive galaxy cluster can distort the light from a far more distant galaxy behind it, stretching its image into faint arcs and rings, or even creating multiple copies of the same object in the sky. For our photon, this means the ruler-straight path we imagine can be gently or dramatically curved by unseen concentrations of mass. Its journey is not a simple line, but a thread woven through the warped tapestry of the cosmos. These interludes, these brushes with dust and gravity, are not merely obstacles to a pure signal. They are transformative encounters, each one layering new information onto the photon story. It becomes a living record of the interstellar medium, a witness to the invisible architecture of space itself. Now, after eons in a stellar core, millennia escaping it, and centuries or more in the galactic wilderness, our messenger finally approaches a singular point of interest, a small, watery world wrapped in a thin, protective veil. The straight line is about to end, not in emptiness, but in an encounter with an atmosphere, a realm where light meets life. The photon's 8-minute sprint ends in a silent collision with an invisible wall. This is not a solid barrier, but a delicate, swirling veil of gas 100 kilometers deep, our planet's atmosphere. After traveling through the perfect vacuum of space, the photon now re-enters a world of matter, and this final atmospheric gauntlet will determine its ultimate fate. The atmosphere acts as a sophisticated security filter for our planet. High-energy photons, the same brutal X-rays and gamma rays that began their lives in the stellar core, are the first to be stopped. They are intercepted and absorbed high up by molecules like ozone, a process that silently shields every living thing on the surface from harmful radiation. Our photon, now a gentle particle of visible light, is mostly granted passage, but mostly is the key word. It does not slip through untouched. It immediately encounters a phenomenon named for the physicist Lord Rayleigh, a process so constant we often forget its profound beauty. The photon collides with the tiny molecules of nitrogen and oxygen that make up our air. If the photon is from the blue end of the spectrum, this collision is dramatic. It is knocked wildly off course, scattered in a completely new direction to paint the dome of the sky. This is why the sky is blue. It is the scattered light of the sun, a daily masterpiece created by trillions of photons, just like ours being redirected by the air itself. The direct beam of sunlight, now subtly depleted of its blue light, becomes warmer and redder, which is why sunrises and sunsets glow with those deep oranges and reds. The light is traveling through a much thicker slice of atmosphere, scattering away even more blue. But the atmosphere is a chaotic place. Our photon's path might be further altered by a wandering water droplet in a cloud, scattering it once more into a diffuse gray glow. It might brush against a particle of dust or pollen, or even be absorbed entirely by a thick bank of fog. This layer of air, so vital for our survival, is the last great editor of the photon's ancient message. It filters, colors, and diffuses the pristine stellar signal. Every ray of sunshine that reaches the ground is therefore a twice-filtered relic, first by the star's own photosphere, and now by our planetary shield. Having survived this final atmospheric turbulence, the photon is mere moments from its destination. Its straight line, forged in the void and gently bent by air, now races downward at that immutable speed. It streaks past mountains and skims over oceans, a silent arrow honed over eons, and it is about to strike a target of astonishing biological complexity. It is headed for a living window, an organic camera evolved over millions of years to catch it. The journey across the cosmos culminates in a meeting with the human eye. The final barrier is not stone or steel, but a curved, transparent dome of living tissue, our photon, after a journey measured in millennia, collides with the cornea, the eye's clear outer window. This is not a passive pane of glass. It is a living structure, constantly nourished and kept perfectly clear by tears. The cornea performs the first major act of bending, or refraction, of the light's path, beginning the crucial task of focusing the chaotic rays into order. Passing through, the photon now floats through a watery chamber called the aqueous humor, a clear fluid that maintains the eye's shape and pressure. Its journey is now directed toward a dark opening, the pupil. This is not a static hole, but a dynamic aperture, its size meticulously controlled by the colorful iris muscle that surrounds it. In bright light, the iris contracts, making the pupil a tiny pinhole to limit the flood of photons. In dim light, it relaxes, opening wide to gather every possible scrap of illumination. This is your eye's built-in camera lens setting, adjusting in real time to the universe's brightness. Through this gateway, the photon now meets the lens. This flexible, crystalline structure is the masterpiece of biological optics. Suspended by tiny muscles, it fine-tunes the focus with exquisite precision. These muscles change the lens's shape, bending the photon's path one final, critical amount to ensure its trajectory converges on a single, sharp point at the very back of the eyeball. All of this, the cornea, the fluid, the pupil, the lens, is a flawless system of collection and focus. It is a living telescope perfected by evolution over millions of years, and its sole purpose is to deliver a perfectly focused image of the outside world onto a special screen. That screen is the retina, a layer of tissue thinner than a sheet of paper lining the interior curve of the eye. But here is the profound and often overlooked truth. Up until this exact moment, the photon's entire epic saga has been a story of physics. It was born in a nuclear reaction, scattered through a star, raced across the void, filtered by an atmosphere, and bent by a lens. Yet it remains just that, a physical particle of energy. It has been transported with incredible fidelity, but it has not been seen. The eye is the collection device, a biological camera of astonishing design. But the camera does not perceive the photograph. The miracle of translation, the moment this ancient physical signal becomes part of your conscious experience, is about to happen in that fragile, paper-thin film. The journey through space and time is over. The journey into the mind is just beginning. The retina is not a screen, it is a translator. That perfectly focused point of light from our photon now strikes a landscape of incredible biological complexity. This paper-thin layer at the back of your eye is home to over 100 million specialized nerve cells called photoreceptors. They come in two distinct types, each with a crucial role. Rods are the specialists of the dim and the shadowy. They are exquisitely sensitive, capable of detecting a single photon of light, and they allow you to navigate a moonlit room or perceive faint motion in the corner of your vision. Cones are the masters of the day. They require brighter light to operate, but they grant you the gift of color and sharp detail. Most humans have 3 varieties of cones, each tuned to a different range of wavelengths that we call red, green, and blue. The entire vibrant spectrum you experience is built from the combined signals of these 3 types. Our photon, having traveled such a vast distance, now faces its final and most intimate challenge. It must be caught. It drifts through the retinal tissue, and if its wavelength is just right, it may be absorbed by a single, waiting pigment molecule. Inside a cone cell, this molecule is called photopsin. Inside a rod, it is rhodopsin. These pigments are the ultimate destination, the biological bullseye for the entire journey. The moment of absorption is silent and instantaneous. The photon does not bounce off, it is consumed. Its energy, precisely quantized and carried across the light years, is delivered in full to this one complex molecule. That energy acts like a key, triggering an exquisitely precise change in the pigment's shape. Think of the molecule as a carefully locked switch. The photon's energy turns the key, flipping the switch into a new position. This microscopic event, this change in a single molecule's architecture, is the pivotal miracle. Here, at this exact point, the universe changes language. A particle of light, a citizen of the realm of physics, ceases to exist. Its journey as light is over. In its place is now a biochemical signal, a message written in the language of chemistry and electricity. The energy that once fused atoms in a stellar core has been transformed into a command that a living cell can understand. It is a handoff of unimaginable elegance, where the ancient power of a star is used to alter the structure of a molecule inside you. This is the fundamental interface, the narrow bridge where the external cosmos meets the internal world of mind. Everything you see, every color, every shape, every glimmer of starlight, begins with this silent, molecular switch being thrown by a traveler from the depths of space. The flipped molecular switch is a silent command that echoes through the entire cell. This single, precise event, where a photon's energy alters the shape of a pigment molecule, triggers a process known as phototransduction. It is a cascade, a chain reaction of biochemical signals designed for one critical purpose: amplification. The cell must shout about the whisper it just heard. Inside the photoreceptor, the altered pigment molecule activates a protein called transducin, which in turn commands another protein to break apart a crucial messenger molecule. The result is a dramatic domino effect. The absorption of that one single photon can lead to the blockage of hundreds of thousands of sodium ions from flowing into the cell. This sudden shift in the flow of charged particles changes the cell's internal electrical voltage. The cell membrane becomes hyperpolarized, a specific shift that is the fundamental vocabulary of the nervous system. It is a binary message, a change in state that says, light has been detected here. Consider the sheer elegance of this biological engineering. A particle of light, which traveled across the cosmos unimpeded, is stopped by a molecule 1,000,000 times smaller than a grain of sand. And from that infinitesimal collision, a signal is born and magnified millions of times over until it is strong enough to be heard by a neuron. The transformation is now complete. The photon's story as a particle of light is finished. What continues forward is no longer about astronomy or physics, but about biology and information. This electrical signal is a data point. It carries encoded information about the presence, the intensity, and crucially, the color of the light that triggered it, all tied to one precise location on the retinal map. But a single data point is not a picture. It is merely one pixel in an image composed of millions. The signal from our photoreceptor is now passed, like a baton, to a network of neighboring neurons within the retina itself. This is where the assembly begins, where the raw, pointillistic data of light and dark starts its journey toward becoming the coherent world you perceive. The message is leaving the eye, traveling down a cable of nerves, and heading for the ultimate interpreter, a 3-pound universe of wet tissue where sensory data is woven into the tapestry of conscious experience. This electrical whisper now enters a network of translators. The signal from our photoreceptor, a single point of data, is passed across a microscopic gap called a synapse to a cell known as a bipolar cell. This cell acts as a relay station, but it is far more than a simple messenger. It begins the crucial work of comparison. Each bipolar cell receives inputs from a small cluster of photoreceptors, not just one. It starts to integrate these signals, looking for patterns in the noise. Is this point of light brighter or dimmer than its neighbors? This fundamental comparison is the very beginning of our ability to detect edges, to see the outline of a tree against the sky or the curve of a letter on a page. The bipolar cell then passes its processed report onward to a final class of neuron within the retina itself, the retinal ganglion cell. These cells are the master integrators. They take the preliminary reports from many bipolar cells and perform even more complex calculations. Some ganglion cells become specialists, firing vigorously only when they detect a specific type of change, like a dark spot moving against a light background. They are not sending a pixel-by-pixel image of the world. They are sending a compressed, pre-analyzed data stream about contrasts, motions, and basic shapes. All of the long, wire-like axons of these retinal ganglion cells now gather together. They bundle into a thick cable that punches through the back of the eyeball. This is the optic nerve, the sole physical connection between your eye and your brain. Our photons information, born in a stellar fusion event and captured by a single molecule, is now encoded into a precise pattern of electrical spikes racing down this biological fiber optic line. It is vital to understand what is and is not happening here. The brain is not receiving a finished picture like a photograph sliding into a slot. There is no tiny movie screen inside your head. What travels down the optic nerve is a torrent of coded dispatches, millions of parallel reports stating things like increase in blue light detected in the upper left quadrant, or a sharp edge moving rightward in the central field. It is a language of contrasts and changes, a live data feed from the front lines of perception. This data cable, carrying the distilled essence of light's ancient journey, now plunges into darkness, heading for the brain's most sophisticated decoding center. The raw message has been delivered. The act of creation is about to begin. The coded data stream now plunges into the brain's deepest traffic hub. The optic nerve does not deliver its signals directly to a vision center, but first to a central relay station buried deep within the brain called the thalamus. More specifically, the information arrives at a pair of small, almond-shaped structures within the thalamus known as the lateral geniculate nuclei. Think of these as the brain's grand central station for visual information. Here, something extraordinary happens. The raw data is not just passed along, it is sorted, prioritized, and integrated. Signals from the left and right eyes are aligned and compared to build depth perception. Basic information about motion and color is separated into distinct processing streams. Crucially, this hub also receives a torrent of feedback from higher brain areas, meaning what you expect to see, what you are paying attention to, can actually influence the very first stages of visual processing in the brain. The signal is already being shaped by your mind before you are even consciously aware of it. From this dynamic hub, the information is finally routed to its primary destination, a thin, wrinkled sheet of neural tissue at the very back of your head, the primary visual cortex. This is where the assembly truly begins, where the brain performs one of the most astonishing acts of natural computation in the known universe. It must reconstruct a world from a river of disjointed reports. This sheet of cortex is not a uniform canvas. It is a meticulously organized factory floor, with different teams of neurons specializing in detecting utterly specific fragments of visual reality. One cluster of cells might fire only when they detect a vertical line in a very precise location in your visual field. Another cluster next door might only respond to a line tilted at 45 degrees. Others are dedicated solely to detecting motion in a particular direction or specific contrasts between colors. They are elemental feature detectors, each one a specialist recognizing a single brushstroke in a grand painting. Through an intricate hierarchy of interconnected processing areas, these fragmented brushstrokes are combined. The outputs of line-detecting neurons feed into cells that recognize simple angles. Those, in turn, connect to neurons that respond to basic shapes like curves or corners. The process cascades upward, with each stage building a more complex representation. The separate streams for color, form, and motion begin to merge. A collection of edges and colors coalesces into the perception of a solid object. The detection of coordinated movement across many points transforms into the perception of something gliding across your field of view. This entire, dizzyingly complex process happens in a fraction of a second, entirely outside your conscious control. It is a silent, relentless construction project, building the stable, coherent world you take for granted from a storm of electrical impulses. And so, in this final neural symphony, the photon's epic journey finds its ultimate purpose. The energy released from a hydrogen fusion event over 8 minutes ago, filtered by an atmosphere, focused by a lens, and captured by a single molecule, has now triggered a specific, intricate pattern of activity across millions of neurons in your visual cortex. That unique pattern is what your conscious mind interprets not as neural firing but as experience. It reads that pattern and understands there is a small, bright, twinkling point of light in the dark sky above. The external, physical reality of a distant star has been successfully translated into your internal, subjective reality. You have not simply received light, you have woven a story from it. The cosmos has sent a messenger, and your brain has written the message it carries. That coherent world you perceive is a carefully constructed illusion of the present. When you gaze up at the night sky, you are not looking at the universe as it currently exists. You are reading a history book written in light, where every entry has a different publication date. The photon that just triggered a thought in your visual cortex is not a messenger from the now, it is an emissary from the past. Its journey time is the delay in the signal, a built-in latency between the event and your experience of it. The bright star Sirius, the dog star, shines from a distance of 8.6 light-years. The light now striking your eye left that star's surface 8.6 years ago. You see Sirius not as it is tonight, but as it was when you were living a different chapter of your life. This delay is not an error, it is a fundamental feature of how we connect with the cosmos. Every point of light above you carries its own unique timestamp. The red giant Betelgeuse might be showing you a snapshot from the late Renaissance. The Andromeda Galaxy, a faint smudge to the naked eye, is a portrait from 2.5 million years ago, from a time when early humans were first crafting stone tools. Your vision is not a live broadcast, it is an archival footage reel, and every object is on a different delay. This transforms a simple glance upward into an act of cosmic archaeology. The night sky is not a flat canvas but a deep, layered excavation site. You are simultaneously seeing stars as they were decades, centuries, and millennia apart, all presented together in a single, silent moment. This is the ultimate meaning behind the astronomer's most powerful tool. A telescope is not merely a device to make faint things bright, it is a genuine time machine. By gathering the ancient light from profoundly distant galaxies, we can peer back through eons. The Hubble Space Telescope's deepest field images capture galaxies as they were over 13 billion years ago, mere infants in cosmic terms. We are witnessing their formative years, a chapter in the story of creation that unfolded long before our sun or Earth even existed. To look up and understand this is to feel a profound shift in perspective. You are not separate from the universe looking in. You are a point within it, receiving messages on a great delay, stitching together a story of what was in order to comprehend what is. The simple, beautiful act of stargazing becomes a direct conversation with deep time. The star you see is not a single story, but a chorus of countless voices. Our journey followed one photon, a single thread in an unimaginably vast tapestry. But your vision is built from a torrent of these threads, a steady, silent rain of particles arriving every second. Each one is a unique traveler with a subtly different biography. While our example photon took a particular zigzag path through the stellar core, its neighbor might have spent a few extra centuries in that chaotic pinball game before escaping. Another may have grazed a different interstellar dust cloud, being reddened just a fraction more than the rest. They do not arrive in a uniform parade, but as a chaotic crowd of individuals, each bearing tiny variations from their epic voyages. Your eye and brain perform a miracle of averaging. They do not process each photon's unique saga separately. Instead, your retina gathers this statistical rain over a fraction of a second. It counts, it compares, it smooths out the random noise. From the jittery arrival of trillions of individual points of light, your visual system constructs a single, stable, unwavering point of light in the sky. This statistical nature is not a flaw. It is the very foundation of how light behaves at the quantum level. At its most fundamental, light is both a particle and a wave, and what we perceive as a steady glow is the probabilistic outcome of countless quantum events. The star does not flicker wildly because the law of large numbers ensures a smooth average. Much like flipping a coin 1,000,000 times will yield a result very close to 50-50, even though any single flip is utterly unpredictable. This collective averaging even defines the colors you see. That pinpoint of white starlight is not one color but a precise blend. Your 3 types of cone cells are constantly conducting a silent census. They count how many red wavelength photons arrive versus green versus blue. The perception of white is your brain's interpretation of a particular balance, a specific ratio in this photon democracy. If slightly more photons from the red part of the spectrum survive the journey, the star appears to have a reddish hue. If more blue photons make it through, it leans toward blue. This simple counting mechanism is the key to one of astronomy's most powerful tools, spectroscopy. By using a prism or a grating to spread a star's light into a full rainbow spectrum, astronomers can conduct an exquisitely precise photon census. They look for fine, dark lines where specific colors are missing, lines that act as a chemical barcode. Each pattern of missing light corresponds to atoms in the star's outer atmosphere absorbing those specific photons. In this way, the collective story of billions of photons reveals the star's composition, its temperature, its motion, and even the presence of magnetic fields. The individual journey is a breathtaking epic of physics, a tale of escape and endurance, but it is in the chorus, in the combined narrative of countless such journeys, that the universe whispers its deepest secrets. We decode the cosmos not by listening to one traveler's tale, but by understanding the patterns of the entire caravan. Your vision is a masterpiece of biological editing. The vibrant world you perceive is not the full reality, but a carefully selected slice, a narrow window opened by evolution onto an overwhelmingly vast spectrum of energy. Our photon's journey began as a ferocious gamma ray, was stepped down to an X-ray, then to ultraviolet, before finally becoming the visible light that escaped the star. But that story could have unfolded differently. With a little less starting energy, it might have been born as an infrared photon, a gentle warmth radiating from a cool, red dwarf star. With even less, it could have been a microwave or a radio wave, a whisper from the cold, dark clouds between the stars. Every single moment, right now, you are being bombarded by these invisible messengers. They pass through you, around you, carrying tales your eyes were never built to read. Cosmic explosions emit torrents of X-rays. Vast nurseries of newborn stars hidden behind thick dust glow brightly in the infrared. The faint, cold echo of the universe's birth, the cosmic microwave background, is a constant radio whisper from every direction in the sky. An entire symphony of the cosmos is playing, but our biological ears are tuned to hear only one single note. This is not a flaw, it is a profound adaptation. Our eyes evolved to be exquisitely sensitive to the specific wavelengths where our sun emits the most light. We see the world in the band of energy that penetrates our atmosphere effectively and provides useful information for survival, like the color of ripe fruit or the subtle expressions on a face. It is a view perfectly curated for life on this planet, but it is a view that hides far more than it reveals. To read the other chapters of the photon story, we had to build new eyes. We sent the Chandra X-ray Observatory into space to see the violent, million-degree remnants of exploded stars. We launched the Spitzer Space Telescope to peer in infrared light through cosmic dust, witnessing the hidden birth of solar systems. And now the James Webb Space Telescope acts as our ultimate infrared eye, gazing back to the first galaxies and analyzing the atmospheres of distant worlds. These instruments are not merely bigger versions of our own eyes, they are translators for wavelengths of light our biology ignores. They reveal that what we call reality is merely the fraction of the signal our particular sensors can decode. The universe is infinitely richer, stranger, and more detailed than the curated show presented to your conscious mind. Your perception is a personal interface, a user-friendly display that simplifies an impossibly complex data stream into a world you can navigate. The true cosmic landscape remains, for the most part, invisibly vast. The photon's final act is one of total surrender. Having traveled across the cosmos to reach this precise molecule in your eye, it does not bounce away or linger. It is absorbed completely, its quantum of energy delivered in full. In that instant, the photon as a distinct entity vanishes from the universe. Its journey, which spanned eons and light years, is over. But as with the fusion reaction that birthed it, nothing is truly lost, only transformed. The photon's energy does not disappear, it is converted. This energy first performs its crucial work, flipping the molecular switch that triggers the vision cascade. Yet after that signal is sent, the energy itself continues on a new, inward path. It degrades step by tiny step into the gentle warmth of your own body. The energy that once powered a star becomes quite literally part of your heat. This is a physical fact, not just a poetic idea. In a very real, metabolic sense, the energy from starlight is constantly being incorporated into your biological functions. Every time you feel the sun's warmth on your skin, you are not just sensing light, you are gathering its ancient energy to fuel your own life. This complete transformation marks the ultimate closure of the epic journey. The cosmic messenger has delivered its package, and in doing so has become one with the receiver. From the universe's vast perspective, the photon's purpose is fulfilled. It transferred energy and information across unimaginable distances to a point of awareness, an intelligent observer capable of wondering about its origin. You are not just a passive viewer of the night sky, you are its active participant. The atoms that construct your body were forged in ancient stellar furnaces, and the energy that animates your thoughts is continually refreshed by the light of our local star. To look up at the stars, then, is to feel a profound kinship. You are made of the same stuff, powered by the same fundamental processes. The separation between you and the cosmos is an illusion of scale. You are the universe in one particular location, momentarily arranged to look back upon itself and tell the story of the light. Your experience of that starlight is profoundly personal, yet it is also a singular chapter in a much larger story of perception. The human eye is a remarkable instrument, but it is only one design among countless others shaped by evolution. For other creatures sharing this planet, the very same photon from that distant star would complete a radically different journey, one ending in a sensory universe we can scarcely comprehend. Consider the common honeybee. To our eyes, a sunflower is a bright yellow disk with a dark brown center. But to the bee, that same flower is a vibrant landing strip painted in ultraviolet patterns, invisible guides that lead directly to the nectar. The photon that would simply contribute to yellow for us might, for the bee, trigger a receptor tuned to a whole other dimension of color, revealing a bullseye or a pathway we are blind to. This is not a minor difference, it is an entirely separate visual reality constructed from the same physical light. The universe broadcasts across all wavelengths, and each species evolves to tune into the channels most critical for its survival. For the pit viper, the journey of a photon takes a dramatic turn away from visible light entirely. Specialized organs on its face act as exquisite heat detectors, capturing the infrared radiation, the warmth, emitted by living bodies. For this snake, a photon born as infrared radiation from a mouse's body completes a short but vital journey, allowing the snake to see the precise shape and location of its prey in pitch blackness. Here, the source of the photon is not a star millions of years away, but the body heat of another animal just a few feet distant. The journey's purpose shifts from cosmic navigation to immediate, life-sustaining hunt. Then there are the masters of color, the Mantis shrimp. These dazzling crustaceans possess not 3, but up to 16 distinct types of color receptors. Where our brain blends 3 inputs to paint our entire rainbow, the Mantis shrimp's visual system is a mystery of staggering complexity. They may perceive colors for which we have no name, a world of subtle gradients and polarized light patterns that transform their reef environment into a kaleidoscopic tapestry far beyond our imagination. For them, a single beam of sunlight penetrating the water is not a blend, but a rich spectrum they can dissect into components we cannot access. This incredible diversity of sight forces a humbling and beautiful realization. The photon's epic voyage from a stellar core is only half the story. The other half is defined entirely by the receiver. The universe sends out a raw, broadband signal of electromagnetic information, a silent symphony playing every note from gamma rays to radio waves. Life on Earth, in its endless creativity, has built a wild variety of biological radios, each one tuned to pick up a different slice of that symphony. Our human consciousness is built to hear a very specific melody, the narrow band we call visible light. But that melody is surrounded by an ocean of other music, songs that other creatures dance to every day. The journey, therefore, is not just a physical path through space. It is a collaborative act of creation between the distant cosmos and the intimate, living sensor that finally catches its message. This biological diversity is a testament to life's creativity, but humanity has taken a unique step further. We have not only evolved eyes, we have engineered new ones. To continue the photon's journey where our own biology reaches its limit, we have built mechanical and digital retinas, instruments that see the messages our flesh cannot. The most fundamental of these is the camera, attached not to an eye but to a telescope. While your retina gathers light for a fraction of a second, an astronomical camera can patiently collect photons for hours, days, even weeks. It holds its electronic shutter open, allowing the faintest trickle of light from the deepest reaches of space to accumulate, one photon at a time, onto its sensor. This process, called long-exposure photography, does what evolution never needed our eyes to do. It waits. It gathers enough of those ancient, weary travelers to paint a picture of objects so distant and dim they are utterly invisible to any living creature. The sensor at the heart of this camera is a technological echo of your own retina. Most modern telescopes use a charge-coupled device, or CCD. This is a silicon chip divided into millions of microscopic light-sensitive wells called pixels. When a photon strikes a pixel, it does not trigger a biochemical cascade but a physical one. It knocks an electron loose. The longer the exposure, the more photons strike, and the more electrons are gathered in each well. At the end of the exposure, the device counts the electrons in each pixel, translating that count into a number, a precise digital value for brightness. In this way, a CCD performs a function remarkably similar to your rods and cones, but with a crucial difference: it never gets tired, it never forgets, and it can share its exact data with the world. This transformation from fleeting light to permanent number is revolutionary. It turns the subjective, momentary experience of vision into objective, storable data. The photon's journey no longer ends in a transient neural pattern. It ends in a spreadsheet, a file that can be analyzed, compared, and transmitted across the planet. But to receive the purest message, we must go to where the message is least corrupted. That is why we launch these artificial eyes beyond our own atmosphere. Telescopes like Hubble and the James Webb Space Telescope are, in essence, giant cameras in space. By placing their sensors above Earth's protective but distorting veil of air, they avoid the final editorial filter of Rayleigh scattering and atmospheric absorption. They catch the photons in their pristine state before our sky can scatter the blue away or blur the fine details with turbulence. From that silent, airless vantage point, these technological retinas can tune into wavelengths our atmosphere completely blocks, like much of the infrared spectrum. The James Webb Telescope is essentially a gigantic, super-cooled eye designed to see the universe in heat vision, capturing the infrared glow of the first galaxies and the chemical signatures in the atmospheres of distant exoplanets. In doing this, we have become active partners in the photon's epic voyage. We intercept its journey not merely to perceive, but to comprehend. We extend its informational life from a flash in a neural network to a permanent entry in the catalogue of human knowledge. Each digital image from a space telescope is a collective visual cortex for our species, a shared memory built from light that began its travel before our civilization was born. This transformation from particle to data, however, rests upon a deeper and more baffling truth. The photon you catch is not simply one thing. From the moment of its creation to the instant of its capture, it embodies the central enigma of quantum physics, the wave-particle duality. It is a discrete packet of energy, a bullet fired from the stellar core, yet it is also a spread-out wave of probability, a ripple in the fabric of reality. This is not a metaphor, it is a concrete, measurable fact of nature that defines the very possibility of its journey. Think of the photon escaping the star. To travel that vast distance as a pure particle would be like threading a needle across a continent, an impossible feat of precision. But as a wave, it can do something remarkable. It can sense multiple paths simultaneously. This wave nature is what allows light to bend slightly around obstacles, a phenomenon called diffraction, and to create intricate patterns of light and dark bands when it passes through narrow slits, which we call interference. These are the signatures of a wave, not a bullet. So which is it? The baffling answer from countless experiments is, it depends on what you ask of it. If you set up an experiment to catch a particle, you will catch one. If you set up an experiment to detect a wave, you will find one. The photon seems to adapt to the question, existing in a blurred state of potential until the moment it is finally measured. And in the context of our story, that final measurement happens in the retina of your eye. Some interpretations of quantum mechanics take this even further. They suggest that until that absorption occurs, the photon's specific path from the star to your eye is not a single, determined line. Instead, it explores every possible route simultaneously, a ghostly superposition of histories. It is only at the instant it is caught that one specific history, one particular thread through space and time, snaps into place as the realized past. This does not change the grand, classical description of its 8-minute voyage, but it adds a layer of profound and beautiful mystery to the very foundation of that journey. The universe, it seems, operates on two sets of rules. There are the large-scale, predictable rules of gravity and motion that guide the star and the planet. And then there are the quantum rules, counterintuitive and fuzzy, that govern the fundamental particles like our photon. These quantum rules are not a bug in the system, they are the essential code. The wave-like behavior is precisely what allows light to be emitted and absorbed in discrete packets. The probabilistic nature is woven into the heart of nuclear fusion itself. That the world feels solid and predictable to us is a miracle of statistics, the smooth average of uncountably many quantum weirdnesses. So when you look up at the night sky, you are not just seeing ancient light. You are witnessing the quiet triumph of quantum logic, a set of rules so strange they defy the intuition born from our macroscopic world, yet so perfectly tuned they allow a message from a star to become a thought in your mind. These unbreakable rules of the road are not human inventions but universal constants. The entire epic you have just followed, from fusion to perception, was sculpted by a handful of immutable numbers woven into the fabric of reality itself. The first and most famous is the speed of light, represented by the letter c, a cosmic speed limit of 299,792,458 meters per second. This is not merely a fast velocity, it is a fundamental property of space-time, the ultimate exchange rate between energy and mass. It is the reason a photon's journey across the light years takes years, creating the cosmic time delay that lets us peer into the past. But c does not work alone. It is partnered with Planck's constant, a tiny number that governs the quantum world. This constant determines the precise packet of energy, the quantum, carried by our photon. It is why light comes in indivisible pieces, and why a specific wavelength of blue light delivers exactly the same energy whether it comes from a star or a light bulb. This quantum rule is the reason your retinal pigment molecule can be so exquisitely tuned. It is built to catch a very specific sized packet of energy, and Planck's constant ensures that packet is always delivered consistently across the universe. Then there is the gravitational constant, which dictates the strength of gravity's pull. This force shapes the star's core, creating the pressure for fusion, and later warps the photon's path through the gravitational lensing of galaxies. These constants are the silent architects of every single step. They are the fixed points in the cosmic blueprint, and here is where the story becomes not just awe-inspiring but deeply mysterious. The values of these constants appear to be breathtakingly fine-tuned. Physicists have discovered that if the strength of gravity were even a tiny fraction stronger or weaker, stars would either burn out in a flash or never ignite at all. If the strong nuclear force which binds atomic nuclei were slightly different, hydrogen might not fuse into helium and the stellar forge would be cold. If the speed of light were significantly faster, the intricate balance of forces that allows for complex chemistry, and thus for life, might never have emerged. The photon's successful journey from a stable, long-lived star through a transparent atmosphere to be absorbed by a molecule in a living eye relies on a cosmic coincidence of staggering precision. This is not a single lucky break, but a chain of perfect conditions. It suggests that the universe operates with a set of rules precisely calibrated to allow for the existence of stars, planets, and ultimately, observers who can trace the path of the light. Some scientists and philosophers see this as pointing toward a profound anthropic principle, the idea that the universe we can observe must be compatible with the existence of observers. We are here to tell the story of the photon because the constants of nature allow for stories to be told. The photon's thread, therefore, is more than a path through space. It is a line drawn by the deepest laws of existence, laws that seem to whisper of a cosmos built with the potential for connection, for witness, and for understanding. This deep resonance between physics and meaning did not begin in a laboratory. For thousands of years across every continent, human cultures looked to the sky and wove the essence of light into the very core of their understanding. Long before we could measure its speed or split it into a spectrum, we recognized light as the fundamental antagonist of chaos and the herald of order. The daily victory of the sun over darkness was not just a celestial event, it was a cosmic drama repeated in countless myths. In ancient Egypt, the god Ra sailed his solar bark across the sky, battling the serpent of chaos, Apophis, each night to ensure the dawn. For the Greeks, Apollo drove his chariot of fire, bringing not just illumination but reason, music, and healing. These were not merely stories about a bright object in the sky. they were profound declarations that light was synonymous with life, law, and divine intelligence. This symbolic connection extended far beyond the sun. To see the light has always meant to attain understanding, to move from ignorance to knowledge. Truth dawns upon us. We have bright ideas and enlightened minds. We speak of a guiding light or a beacon of hope. These are not arbitrary metaphors plucked from the air. They are linguistic fossils of a deep, intuitive recognition. Our ancestors perceived correctly that light is what reveals the world. Without it, we are blind, lost in a formless void. With it, the shapes of reality emerge, and we can navigate, learn, and build. What they sensed as a spiritual or philosophical truth, we now understand as a precise physical process. That aha moment of understanding, that sudden clarity, is mirrored by the photon's journey. A piece of information encoded in light travels across a void of ignorance, is focused by the lens of our attention, and is finally absorbed and processed by the mind, illuminating a previously dark corner of our comprehension. The ancient intuition that light brings knowledge is, in a literal sense, scientifically accurate. Our vision is a continuous act of gathering data from the cosmos, and our conscious thought is the interpretation of that data. This parallel becomes even more poignant when we consider sacred texts and architectural wonders. Stained glass windows in great cathedrals were designed to transform sunlight into narratives of faith, literally using light to tell a divine story. Monuments like Stonehenge are precisely aligned with the solstice sun, capturing a specific moment of light to mark the calendar, turning astronomy into ceremony. These practices show a human desire to commune with the light, to use its predictable, revealing nature as a bridge to something greater than ourselves. They represent an early, instinctive form of information processing, where the timing and angle of light itself carried meaningful data about the seasons, the gods, or the structure of time. Our modern scientific narrative of a photon born in fusion, carrying stellar data and triggering neural signals, does not erase these ancient stories. Instead, it gives them a new kind of depth and grandeur. It reveals that the poets and priests were responding to a real, majestic phenomenon, one whose full mechanics are more astonishing than any myth. The light they worshipped as a god is in fact a countless stream of messengers from a universal forge, each one a tiny packet of transformed mass on a mission to deliver a piece of reality to a waiting mind. Our drive to build temples to the light and tell stories about it was a pre-scientific expression of the same awe we feel when we comprehend the photon's billion-year journey. It is the awe of a conscious universe in one small part of itself, beginning to understand how the rest of it works. This bridge between the symbolic and the physical suggests that our quest for knowledge, our yearning for enlightenment, is written into our very biology, a direct consequence of being creatures who evolved to read the world in photons. That cosmic narrative is not locked away in distant observatories. It is the very foundation of how we build our modern world. Everything we know about the universe beyond our atmosphere comes from a single, relentless practice, the analysis of incoming photons. Astronomers are, in essence, master translators of light. By patiently collecting these ancient messengers and separating their wavelengths, they can read the chemical composition of nebulae, measure the rotation of galaxies, and even detect the subtle wobble of a star caused by an orbiting planet. This entire science is built upon the final chapter of the photon's journey, the moment it surrenders its information to a sensor. That same principle of capture and conversion drives technology that shapes our daily existence. Consider the solar panel on a rooftop. It is a field of silicon cells engineered to intercept photons from our local star. When sunlight strikes, the energy of those photons is absorbed, not by a biological pigment, but by the semiconductor material. This energy knocks electrons loose, creating a flow of direct current electricity. The warmth you feel becomes power for your home, a direct transfer of stellar energy into human use. On a more intimate scale, the precise understanding of how light travels enables the global network of fiber optic cables. These glass threads act as light pipes, guiding photons from lasers in a pattern of rapid flashes that encode our voices, our messages, and our videos. Your video call with someone across an ocean is a conversation carried by trillions of photons, meticulously directed through a labyrinth of transparent pathways, their journey now orchestrated by human intelligence for the purpose of connection. This mastery extends into the delicate realm of medicine. Surgeons use concentrated beams of photons, lasers, to perform procedures with microscopic precision, sealing blood vessels or correcting vision. Medical imaging technologies like X-rays and MRI scans, though using different parts of the electromagnetic spectrum, rely on the same fundamental concept, sending controlled energy into the body and interpreting the signals that return, building a picture from the way light and other energies interact with our living tissues. Yet the most profound application is also the most personal. It lives in your daily, unremarkable moments. The gentle heat on your face during a morning walk is not an abstract sensation. It is your skin absorbing the infrared portion of the solar photon rain, a direct energy transfer from a nuclear furnace 93 million miles away. The breathtaking palette of a sunset, with its deep reds and oranges, is a live demonstration of atmospheric scattering, a final artistic filter applied to sunlight after its 8-minute sprint. Even the simple act of reading these words, of distinguishing the dark shapes of letters from the bright background of a screen or page, is your visual cortex performing its real-time miracle, reconstructing meaning from a pattern of reflected or emitted photons that completed their journeys mere nanoseconds ago. To internalize this knowledge is to perform a quiet alchemy on the ordinary. It transforms a passive experience into an active recognition. You are not just feeling warmth, you are gathering ancient stellar energy. You are not just seeing color, you are witnessing a physics demonstration in the sky. The boundary between the cosmic and the commonplace dissolves, revealing a world where every beam of light is a story in motion, and you are both its destination and its interpreter. That final translation from particle to perception is perhaps the deepest mystery of all. We have traced a photon from a nuclear reaction to a neural signal with near-perfect physical detail. Yet something extraordinary happens in that final step, something science can describe but not yet fully explain. How does the objective, measurable event of a photon striking a retinal cell give rise to the utterly private, subjective experience of seeing the rich gold of a sunset or the sharp glitter of a star? This is not a question about the mechanics of vision, but about the nature of experience itself. Philosophers and neuroscientists call this the hard problem of consciousness. It asks why and how any physical process, no matter how complex, should be accompanied by an inner life, by feelings and sensations known as qualia. The soft, warm feeling of sunlight on your skin, the specific hue you call yellow, the sense of depth when you gaze at the moon, these are your qualia. They are real to you, yet completely inaccessible to anyone else. The photon's journey builds a perfect bridge between two seemingly separate realms. On one side is the external, objective cosmos, governed by mathematics and physical law. On the other is your internal, subjective universe of color, sound, and meaning. The photon is the courier that crosses the border, but the moment it delivers its package, the message changes language from physics to feeling. This suggests a radical idea that we are not merely passive observers peering out at a universe from which we are separate. We are the universe in one particular arrangement, momentarily looking back at itself. The cosmos, over billions of years, forged stars, planets, and through a long chain of evolutionary events, produced nervous systems capable of receiving its own light and transforming it into story and sensation. Your consciousness is not a ghost in the machine. It may be an emergent feature of the cosmos itself, a property that arises when matter becomes organized in a sufficiently complex and interconnected way. Think of a single musical note played by one instrument. It is a simple physical vibration, but when countless notes are arranged by a composer and performed by an orchestra, something new and immaterial emerges, the profound emotional experience of a symphony. In a similar way, the raw data of a photon's arrival is just a vibration, but when processed by the vast, networked symphony of your brain, the experience of seeing emerges. The photon's path is therefore more than a link between a star and a cell. It is a physical thread in a much larger tapestry that may connect the fundamental mechanics of reality to the phenomenon of awareness. This mystery sits at the crossroads of astrophysics, biology, and philosophy. It hints that the urge to understand the stars is not a detached hobby, but a form of cosmic self-recognition. Every time you look up and wonder, you are the universe contemplating its own origins and its own nature, using the very light it created eons ago as the medium for that thought. The mastery of light is no longer a passive art of reception. We are entering an era where we can reach into the photon's journey and sculpt its path, bending the rules of optics to serve our vision. This begins with a clear challenge: the shimmering distortion of our own atmosphere. For centuries, the turbulence of Earth's air blurred the fine details of stars into twinkling smudges, a beautiful but frustrating veil. The solution is a technology of exquisite feedback called adaptive optics. A powerful telescope does not simply stare at a distant galaxy. It also focuses on a bright guide star, either a real one or an artificial laser spot created in the upper atmosphere. Sensors analyze the distorted shape of this guide star's light hundreds of times per second. In real time, these measurements command hundreds of tiny actuators behind the telescope's primary mirror, subtly deforming its surface to precisely cancel out the atmospheric ripples. It is as if the mirror becomes a fluid, intelligent eye, constantly reshaping itself to see past the chaos. The result is not a minor improvement, it is transformative. Images from ground-based observatories equipped with adaptive optics can rival, and sometimes surpass, the clarity of those from space telescopes, revealing details on other worlds and the hearts of distant galaxies with stunning precision. We are not just looking through the atmosphere anymore, we are commanding it to become still, but our manipulation ventures into far stranger territory than correcting blur. In the quantum realm, we can create pairs of photons that share a mysterious, instantaneous connection called entanglement. When two photons are entangled, measuring a property of one, like its polarization, instantly determines the property of the other, no matter how far apart they have traveled. This linkage, which Einstein famously called spooky action at a distance, seems to defy our classical understanding of space and time. It is as if the photons are not two separate travelers, but two aspects of a single entity. This is not science fiction, it is laboratory routine, and it forms the bedrock of emerging quantum technologies. Quantum cryptography uses entangled photons to create communication channels that are fundamentally unhackable, as any attempt to eavesdrop disrupts the delicate quantum link. The dream of quantum computers relies on manipulating such entangled states to perform calculations impossible for any classical machine. Here, we are engineering not the photon's physical path, but the very information it carries, weaving a web of correlation that transcends distance. Our control extends to the materials light travels through. Scientists are designing metamaterials, artificial structures with patterns smaller than the wavelength of light. These materials can bend light in ways no natural substance can, creating effects like negative refraction, where light bends in the opposite direction from normal. This principle opens the door to technologies once confined to fantasy, such as superlenses that can see details smaller than the wavelength of light, or cloaking devices that can route light around an object, rendering it effectively invisible. We are learning to design the stage upon which the photon travels, dictating its behavior with architectural precision. This trajectory points toward a future where we might engineer the entire journey, from a photon's emission to its final detection. We could create bespoke light sources for medical therapies, design secure global networks using the unbreakable laws of quantum physics, or build telescopes with lenses of perfect clarity. Each advance further dissolves the old boundary between observer and cosmos. We are no longer merely catching messages from the stars. We are beginning to write the rules of the conversation, using the photon not just as a messenger, but as a brush, a key, and a thread in the fabric of a technology we are only starting to imagine. Tonight, when you look up, remember this story. That faint glimmer of light is not just a dot. It is the destination of a traveler that has crossed unimaginable voids and epochs to meet you. You are the endpoint of a cosmic narrative billions of years in the making. This knowledge invites a shift from passive viewing to active participation. You are having a direct physical encounter with a distant sun. Let this understanding deepen your sense of wonder and connection. The universe is not out there. It is actively sending messengers to you, and you are built to receive them. This realization is perhaps the most beautiful gift of understanding the photon's incredible journey. Think of it this way. For most of human history, we saw the stars as fixed points on a distant dome, beautiful but separate, decorations in a sky that felt like a ceiling. But now you know the truth of their motion, their distance, their nature as roaring furnaces. More importantly, you know the truth of their light. That connection is not a metaphor. It is a literal, physical thread. A photon leaves the surface of a star, and after a journey of years or centuries, it is annihilated within a molecule in your eye, its energy becoming part of the signal that builds your thought. You are not looking at history, you are touching it. Your retina is the finish line for a race that began before your ancestors walked the earth. This transforms stargazing from a hobby into a kind of communion. You are not a spectator in a cosmic arena, you are a participant in a continuous, silent conversation. Every time you glance upward, you are accepting a delivery from the universe, a package stamped with a date from the deep past. This active participation changes the quality of the darkness itself. The night sky is no longer an empty space between the bright points. It is the medium through which these ancient stories travel. The blackness is not an absence, but a canvas upon which the universe paints with the light of its own history. When you find a familiar constellation, you are not just connecting dots, you are linking in points of countless journeys, each photon having navigated its own unique path through the gravitational hills and valleys of space to arrive in that specific pattern for you tonight. Your simple act of recognition completes a circuit. You provide the consciousness that gives meaning to the voyage. Without a living sensor to translate its arrival into perception, the photon's epic journey would be a beautiful but untold story, a message sent with no recipient. You are the recipient. Your awareness is the final ingredient that turns physics into poetry. So carry this with you. The next time you step outside on a clear evening, pause for just a moment. Let your eyes adjust to the dark. Do not just see the stars, feel the connection. With every point of light you perceive, you are welcoming a traveler home. You are the universe in one small, curious corner of itself, looking back at the rest and saying, "I see you." And in that seeing, across the vast and silent distances, a bond is formed. It is a bond built not on proximity but on understanding, a thread woven from light and mind. That is the true legacy of the photon's journey. It reveals that we are not isolated observers, but integral parts of a grand, luminous, and deeply interconnected whole. That final, silent meeting between star and sight is a testament to a universe built for connection. We have followed a single thread of light from its violent birth in the heart of a star, through its chaotic escape and lonely marathon across the interstellar sea, to its miraculous translation into the very fabric of our thoughts. This voyage connects the largest scales of cosmic physics to the most intimate scale of human consciousness. It reveals a profound truth: to look at the stars is not a passive act, but an active dialogue with time, matter, and energy. You are engaging in a conversation where the universe speaks in photons, and your mind provides the meaning. Every point of light you perceive is a messenger that has crossed the abyss to reach you, a traveler from a distant past whose journey concludes in the quiet theater of your awareness. This knowledge transforms a simple glance upward into an act of cosmic recognition. You are not merely an observer standing apart from the cosmos. You are a participant woven into its grand narrative. Your eyes are the destination for ancient light, and your consciousness is the stage where the universe tells its own story. So the next time you find yourself beneath a clear, dark sky, remember this journey. Let the weight of that deep time, the elegance of that transformation, fill you with a quiet and enduring awe. You are part of an immense, luminous whole, a singular point where the cosmos turns to look back upon itself. If tracing this epic voyage has illuminated your perspective, please share this video with someone else who gazes at the stars in wonder. Subscribe for more explorations into the deepest mysteries of space, and let us know in the comments which part of the Photon's incredible journey amazed you the most.